All right, we're back with parts B and C for question 6. If t sub s is equal to 0.2s, plot x sub p of j omega. So x sub p of j omega is equal to the Fourier transform of x sub p of t, and that's equal to the Fourier transform. So x sub p of t, we have x of t times this, so let's call this p of t. X of t times p of t. Now p of t is equal to, and actually let's go back over here real quick, 1 second, sorry. So x sub p of j omega, we have a Fourier transform of multiplication, so that gives us convolution in the time domain, or in the frequency domain, excuse me. 1 over 2 pi, that's our scaling factor. X of j omega convolved with big P of j omega, where big P of j omega is the Fourier transform of P of t, and x of j omega is the Fourier transform of x of t, which this is x of t. This is the Fourier transform of x of t. So this is x of j omega right here, as a reminder. So we get that P of t is equal to the summation over all of time of delta of t minus k times ts. And what this is this is an infinite impulse train. So if t is equal to 0 and we go through all of our k's, we will have at k equals 0, we'll have an impulse. And now if t is equal to uh, ts, then at k equals 1, then we'll have another impulse. So this is just going to give us a bunch of impulses spaced out, and between each one is the change in time. Delta t is equal to ts. So this is going to be a delta t where this is equal to ts, and that's going to be between every spot. So we'll just have an infinite impulse train, and we can use that to sample our signal as long as it meets the sampling criteria. But we'll get to that. So if we look if you go to table 4.1, then we get P of j omega is equal to, and it's about halfway down, and we have the signal, which is the infinite impulse train, and that gives us the Fourier transform, which is equal to 2 pi over t. And what do you know? We get another infinite impulse train. We do k equals negative infinity to infinity, and it's delta of omega minus 2 pi k over t. So an infinite impulse train in the time domain gives us an infinite impulse train in the frequency domain. We also could have done a Fourier series for this, but we don't need to because we have our table. It's handy using the tables. But this is a periodic signal, so we could have used Fourier series. But now we can dive into x sub p of j omega, because we know that's equal to 1 over 2 pi times the convolution of x of j omega and p of j omega. So let's write p of j omega over t. K equals negative infinity, infinity, delta of omega minus 2 pi k over t. And we have a constant coefficient right here. So we can bring that up front. We'll have 1 over 2 pi times 2 pi over t. So we end up with 1 over t. And we have x of j omega convolved with a infinite train of delta functions. Now, the shifting property tells us that the convolution of any signal with a delta function is equal to that signal evaluated at this argument here. So we have x sub p of j omega, it's equal to 1 over t, and it's going to be x of j omega minus 2 pi k over t. And, oh, I forgot something pretty important there. We got to do the summation. So the summation is, this is a linear operator. So we can actually pull that out front too. I could have done that. I might make it a little more clear if I do it in this step. It's a linear operator, so I'm going to pull it out front. So we have 1 over t. That's from 2 pi over t times 1 over 2 pi. And then we have this summation here. It's a linear operator because it does not, there's nothing in x that depends on k. If we had something in x that depended on k, then it might not act as a linear operator, but in this sense it does. So we have k equals negative infinity to infinity, and we have x of j omega convolve with delta of omega minus 2 pi k over t. And like I said, now we apply the shifting property and we get this here, sum over all of time, or all of k rather, and it is x of j omega minus 2 pi k over t. And if we wrote out a couple terms where t is equal to 0.2, so t is equal to 0.2, so 1 over t is equal to 1 over 2 over 10, which is equal to 5. All right, so 1 over t is equal to 5. We could write out, we'll do a couple terms here, dot, dot, dot. We'll do plus x of j omega minus, or plus, because this is for k equals -1, it would be 10 pi plus x of j omega, this is k equals 0, plus x of j omega minus 10 pi, this is k equals to 1, plus x of j omega minus 20 pi, and plus dot dot dot, plus dot dot dot, and this is k equals 2. So what we have is we just have a replica of our signal x of j omega, and we have that replica. We have one of them at the origin, right? And then we have this little apex here, and we just have this replica every 10 pi, just up and down time. So if we come here and let me move this up. Right, and then well, here's our replica. Here's x of j omega. So we have one there. Yeah, close enough. And then we'll have another one here. Here's where's 10? There's 10 right about there. And we're going from 6 pi to 14 pi, which 14 pi minus 6 pi is 8, and we have 4 pi minus -4 pi, that's 8. And then we'll have another one. We'll have another one. Man, this is being laggy. We'll have another one there. That's a little bit off from where it's supposed to be. And then we'd have a whole bunch in the negative direction. And I think you get the picture. And dot, dot, dot here to indicate that it goes on forever. And as you can see, we have no overlap between our signals. We have a 2 pi spacing right there, a 2 pi spacing right here, a 2 pi spacing right here, because there's 14 pi and 16 pi, 4 pi and 6 pi, -6 pi, -4 pi. So we have no aliasing occurring. Excuse me. Now for part C, for what values of T of S would aliasing occur? So we have the Nyquist theorem, which states that the sampling frequency, in order to prevent aliasing, the sampling frequency has to be at least 2 times the maximum frequency. Okay, so uh, and we can look right here and see that if we single out x of j omega, and let's just look at it right here, we have x of j omega. Well, what's our maximum frequency in this? Our maximum frequency in this is 4 pi, because this is the frequency domain. So this is the frequency axis, and we can see that's 4 pi. So that's our maximum frequency. So we have the sampling frequency must be greater than 2 times the maximum frequency in the signal. So we have omega sub s must be greater than, well, it'd be 2 times 4 pi, which is equal to 8 pi. And let's divide both sides by omega s and 8 pi. Then we get 1 over 8 pi has to be greater than 1 over omega s. Now, omega s is equal to Ts divided by 2 pi. Did I do that right? So we have 2 pi f is equal to omega s, which is equal to 1 over t. And then if I divide by, I get omega s over 2 pi is equal to f, right, which is equal to 1 over t. Yeah, so I did that right. So, and let's write that right here. 1 over 8 pi must be greater than or equal to t sub s over 2 pi, which we bring that over here, multiply both sides by 2 pi. We get 2 pi over 8 pi, so we get 1 over 4. Must be greater than t sub s. So our sampling period has to be smaller than, so sampling period t sub s must be smaller than 0.25 seconds in order to prevent aliasing. And we can see that we don't have much room in here anyway, and this was with our sampling period being 0.2. Obviously, if we increase our sampling period, we have more space in between our delta functions, our impulses that are sampling our signal. So if we did have, let's say that t was equal to 0.5, then if t was equal to 0.5, then we would have all these 10 pi's here. These 10 pi's here would be equal to, this would be 4 pi, this would be a 0, this would be a 4 pi, this would be an 8 pi, and we'd be running into each other. We would be running into each other because we have another sample. We would be sampling again, right here. And then again right here. And what that would look like is we'd have something. Actually, it wouldn't even do that. It would just be, but all of this would be well above 0. So we would not be getting replicas of our original signal. All right, that's that one, and I'm gonna call it quits for the night, and I'll be back tomorrow when I'm a little more on the ball. Thanks.